Nature of motion under central force. Nature of motion under central force. A central force obeying inverse square law is in general represented as Fr equal to plus minus C upon R square. Plus minus C upon R square. The positive sign being taken for a repulsive force. Positive sign being taken for a repulsive force. Which force? Repulsive force. Repulsive force. Repulsive force. And minus sign and a negative sign for an attractive force. And attractive force. Attractive force. Minus sign and attractive force. The corresponding potential energy is given by U equal to minus integration of function R dr. Then the value is minus plus C upon R square dr equal to, we are calculating this value, the value is plus C by R. This is the equation number 1 for a repulsive force. This is the for repulsive force. And for an attractive force, U equal to minus function of R dr. Then the value is minus integration of minus C upon R square. Minus sign represent the attractive force. So this value is minus C upon R square dr equal to minus C by R. This is the equation number 2. The total energy of a particle moving under a central force is given by, the total energy of a particle moving under a central force is given by E equal to 1 upon 2 m differentiate of R square plus J square upon 2 m R square plus U. This is the equation number 3. And we can solve this problem is 1 by 2 m differentiate of R square plus J square. J is the angular moment. J square upon 2 m R square plus minus C upon R. This is the equation number 4. Where C by R is the potential energy. C by R is the potential energy. C by R is the potential energy. Due to inverse square law of force. Due to inverse square law force J square upon 2 m R square equal to 1 upon 2 m R square differentiate of theta square, the potential energy associated with the centrifugal force, and 1 by 2 m differentiate of R square and 1 by 2 m differentiate of R square, the radial kinetic energy. This is the radial kinetic energy. This is the radial kinetic energy. And effective potential energy. Effective potential energy. Effective potential energy U dash equal to U plus J square upon 2 m R square. Hence equation third can be written as equation third can be written as E equal to 1 upon 2m differentiate of r square plus u dash. First is a repulsive force. First is repulsive force. Repulsive force. First is repulsive force. Repulsive force. U equal to plus c upon r as j square upon 2m r square is always positive. U dash is always positive quantity and hence E is positive. But this is always positive. This is always positive. This is always positive. This is always positive. Then the U dash is a positive. U dash is a positive quantity. And hence E is plus E is positive. Second number, zero force. Second number, zero force. Second number, zero force. Second number, zero force. Zero force means for no force. U equal to 0 and U dash equal to j square upon 2m r square is positive. Is positive and E is positive. And the third number for attractive force. Third number, attractive force. Third number, attractive force. For an attractive force, U equal to minus c upon r and U dash equal to j square upon 2m r square minus c upon r. The variation of j square upon 2m r square with r is shown in the curve first. We can draw a curve. This is the axis. And this is the vertical line, and this is the horizontal line. This is the vertical line, and this is the horizontal line. Then this is the horizontal line. It represents R, and first this is the minus E energy. And this is the plus E energy. Then the first number curve. That means first case. This is the plus E line curve, and this is the minus E line curve. And this is the E line curve, and this is the helping line. Then first number curve is a j square upon m r square 2m r square. Then the curve is starting from here and going to this as light. This is the first curve, and the second curve is and this line is E equal to E1, and this line is E equal to E2 equal to 0, and the second curve is starting from here and going to going to as like this, So U equal to minus C upon R. This is the attractive force. For this attractive energy equal to minus C upon R. And the third curve is starting from here. Third curve is starting from here and going to as this is a show. Then the value is this is the point A. And the distance from plus E to A is R. A is R1. And this is the point. This is the point B. This is the point B, and this is the value is R2. This is the value is R2, and the crossing point this is here. This is the point C, and the value of this is R3. Value of this curve is R3, and this is the second point C dash. This is the second point C dash, and this is the R3 dash. This is the distance is R3 dash, and main point is this point is as like this. This is point D, and this is R0. R naught. This line is so that second curve, and this line is E equal to E4 equal to E minimum. Then the value is the variation of J square. The variation of J square upon 2mr square equal to minus with R is shown in the figure 2.3 first point. 2.3 first point. This is the first point. J square upon 2mr square. This is the first curve, and the variation of minus C upon R, and the variation of minus C upon R with R is shown in the second curve. This is the minus C upon R curve. As U is a negative quantity, U dash can have positive, but U dash can have positive 0 or negative value. Positive 0 or negative value for C upon R. C upon R is less than J square upon 2mr square. U dash is positive for C upon R. U dash is positive for C upon R. And U dash is 0. Then C upon R is the greater than J square upon 2mr square, and U dash is negative. The variation of U dash, the variation of U dash, the effective potential energy with R is shown in the figure. Third number curve. For negative value of U dash, the total energy is positive. For negative value of U, total energy is positive, and U dash is less than 1.2 m. R differentiate of R square. E is 0 for U dash equal to 1/2 mr square, and E is negative for U dash is greater than 1/2 mr square. Hence, three cases arises corresponding to total energy E positive, 0 or negative. Case number first. First case. In first case first, total energy is positive. total energy E is positive. Total energy is positive. That means suppose the particle has a total positive energy E equal to E1. Suppose the total energy E equal to E1, the particle comes from infinite where R equal to infinite and U dash equal to J square upon 2 mR square minus C upon R equal to 0 and E equal to E1 equal to 1 upon 2 m and differentiate of R square. As the particle travel from infinite to the other mass, U dash first becomes negative. U dash first becomes negative, reaches a minimum negative point value and then goes on increase till U dash E for R equal to R1 at A as shown in the figure, and the particle cannot come closer than R1. The particle cannot come closer than R1 because U dash will be greater than E1. U dash will be greater than E1. U dash will be greater than E1. And E1 minus U dash will be have a negative value, but E1 minus U dash equal to 1 upon 2 m differentiate of R square. The radial kinetic energy which must always be positive. Thus the region to the right of A is entirely accessible to the particle, and the region to the left of A and the region to the left of A is strictly forbidden. The point A at which the radial kinetic energy vanishes is called the turning point. And such a motion will be unbounced. The particle will come from infinite and go up to R1 and return back to infinity. The path is hyperbolic. And second case number second. 1 minute. Second case. The total energy is 0. The total energy E is 0. Suppose the particle has total energy E equal to E2 equal to 0. In this case, its energy line coincide with R. In this case, suppose that the particle has total energy E equal to E2 equal to 0. In this case, its energy line coincide with R axis, and there is only one turning point at B. Where OB equal to R2, where OB equal to R2. The value of R2 being greater than R1. The motion of the particle is still unbounded. The path is parabola. Parabola path. And case number third is total energy is negative. Total energy E is negative. negative. In this case, we shall deal with two different situations. First number, suppose the particle has a total negative energy E equal to E3. E equal to E3. Suppose the total energy E equal to E3. E equal to E3. Total energy E equal to E3. Suppose that the total energy line for E3 cuts curve for U dash, cuts curve for U dash, cuts curve for U dash, U dash, cuts curve for U dash, and at 2 point C and C dash, at 2 point C and C dash, C and C dash corresponding to radial distance R3 and R3 dash, corresponding to radial distance R3 and R3 dash. Thus there are two turning points at this point. U dash equal to U dash equal to U dash equal to 1 upon 2 m differentiate of I square. The radial kinetic energy, the region R is the less than R3. The region R is the less than R3. The region R is the less than R3. R3 and R is the greater than R3. Then the R is variation from R3 to R3 dash. R is variation from R3 to R3 dash. R is variation from R3 to R3 dash. R3 dash are forbidden and the motion of the particle is bounded in the region R3 dash. R3 to R3 dash. R3 to R3 dash. R3 dash. The path is ellipse. The path is an ellipse. The path is an ellipse. Ellipse. The path is an ellipse. Ellipse. Second case. Suppose the particle has total negative energy E. Total negative energy E equal to E4. So that the total energy line for E4 meets the curve for U dash. Meets the curve for U dash at the minimum point D. At the minimum point D. At the minimum point D corresponding to radial distance R0. Corresponding to radial distance R0. Corresponding to radial distance R0. The value of R at which U dash has a minimum value can be calculated by equating. Rest of 1 minute. du dash upon d are equal to 0 r d upon d r in bracket close j square upon 2 m r square minus c by r, bracket is closed and 0. Then the r minus j square upon m r cube plus c upon r square equal to 0 r equal to j square upon mc. This is the equation number 6. This is the equation number 6. So, minimum value of r equal to r0 equal to j square upon mc. J square upon mc. The minimum total energy corresponding to r0 is given by E minimum equal to U dash minimum equal to j square upon 2mr0 square minus c upon r0. The value is mc square upon 2j square minus mc square upon j square equal to minus 1 upon 2 mc square upon j square. Hence, when E equal to E4 equal to U dash minimum, the motion is possible only at one radius R0. At only one radius R0. The orbit is a circle of radius R0 equal to j square upon mc. When E equal to U dash minimum, then the value is j square upon mr cube equal to c upon r square From the equation number, from the relation 6. But but C upon I square is the central force obeying inverse square law of inverse square law inverse square law Fr. So the value is Fr equal to J square upon mr cube equal to mr square differentiate of theta square upon mr cube equal to mr differentiate of theta square. The force is just equal to the centrifugal force required for a circular motion. Hence, when E lies between minus mc square upon 2j square minus mc upon 2j square and 0 the motion is elliptic with two turning points at r equal to r3 and r equal to r3 dash. The distance r3 dash and r3 dash called apsidal distance for energy less than E4 equal to E minimum. No solution of a problem is possible and the condition cannot be realized physically. Thus, for bounded motion, the total energy E must be negative. But not less than E minimum equal to minus 1 upon 2 mc square upon j square. In other words, for bounded motion, E is less than 0 and 0 is less than E and is greater than minus 2 upon mc square upon j square. This is the equation number 8. This is the equation number 7. This is the equation number 7. Okay. Thank you.